Okay, now we start with the section named your code, that is line number 48. Now we say first we initialize DS. So DS will have a read-only segment which is 0x, which is stored in 0x18. So let us say where will 0x18 descriptor be stored? We know that the GDT starts at D1000, so we will do s/2x 0x D018. There you see that there is a descriptor starting at B1000 of limit 512 bytes, and you see here it is 409, so it is privilege 0, but it is a, and the type is 0, so this is a privilege 0 read only data descriptor. So for details of this we can actually even see here. So for the segment descriptor, so type 0 is a read only data descriptor, as you see here. And for you to understand, again just going back to what I had covered earlier, for you to understand how the descriptor looks like. So this is the structure of the descriptor. So the base address here and the segment address limit here, part of segment limit here, part of base address split across 3 places. So just remember this or try to note this so that you could interpret this. So now we have a read-only descriptor at B1000 of size 0x200 and privilege 0. So let us go and make a note of it here. So 0x18 in GDT is a read-only data seg starting at B1000 at limit 0x200. So similarly, let us go and say what is 0x20. I am in line number 50 here, and that you see that it is again a B200, but note that this is now of type 2. This is a read-write segment starting at B1200 of size 0x200. So your 0x20 in GDT is a read-write data segment starting at B200 and of size 200. Now what is B28? Again I am doing x/2x here. Note that it is again a read-write segment of privilege 0 starting at B400 and of size. So let us do the same thing again here. $400. Now what is 30 now? 0x30. This is B1600, again it's a read-write segment. And what is B038? Please note that this starts at C1000 in this of size 0x40, hexadecimal 40, which is 64 bytes, and it is type 6. What is type 6? Let us go to this and see what is type 6. The type 6 segment is read, write, expand, down. Okay. So we will just see that this is, go back to this, sorry. Okay, so this is type 6, so 0, and it starts at 3000 and of size 40. Then you make the ESP. Then you make the ESP as 80, which is very important. So we make ESP as 80. Now we make okay. Now before we, and EBP also has 80. Okay, so we have come to line number 59. Now before we start working on the line 61 and above, 61 and this thing, let us now look at this code starting at 75. 75 is basically the matrix multiplication algorithm. Okay. So when I execute a call matrix multiplication, what will be there on the stack is the return address. So what we are doing here is, first we will pop the return address and store it in EBX. And we will just use we will make ECX as 0, right? And what we are going to store is, we are storing the return address into the location GS:0x80. So what is GS? GS starts at B1600, right? So in B1680, I am going to store, in B1680, I am going to store the return address. So every time I call matrix mail, so I'll just put a session like this, working of matrix mult, store return address at 0xB080. Okay. Now, before going to this part of the code, we will just finish off the easier part, which is I start. So let us look at the matrix multiplication code. The matrix multiplication code is, for I equal to 0 to 10, j equal to 0 less than 10, make Cij equal to 0. For k equal to k less than 10, Cij is equal to Cij or Aik into Pkj. Right? So there is an I loop variable, there is a j variable, there is a k variable. So for all these I, j and k, we need to have general purpose registers. Right? So when we look at it, my ECX, so this is I have made a comment I start, j start and k start. this C code is the C code starting from I start going till I finish. Okay. So now let us see what the C code essentially means before we go back to the code before this I start. So ECX is a loop variable which is representing I, which stores the value of I. ESI is a loop variable, it represents the value of J. And EDI is a loop variable which represents the value of K. So initially I have made ECX as 0 long back. Here itself I made ECX as 0. Now what I do here is, every time I compare ECX with 10. If it is equal, this is called JE. JE means if jump and equal. If it is equal, I go to I finish. I finish is at the end of the code. This is something like I finished the entire program. I finished the matrix multiplication. I go to I finish. But if I am not, if ECS is not equal to 10, then I start a J loop, ESI equal to 0. I make J equal to 0 here. Again this is J start. Every time I compare J with 10. If J becomes equal to 10, jump on equal to, I go to J finish. J finish is here. Otherwise what I do? I move EDI 0. I make K as 0. DDI stands for K. And I have to make Cij equal to 0. Right? That's what this code says. Cij is equal to 0. Initially, I store Cij in some temporary location. Again, it is B1700. GS is B1600. So this will be B1700. So, so in the matrix multiplication, store the local, the intermediate Cij's in 0xb6, right. So this is going to be 100, B700. Sorry, this should also be store return address at B680. Right, that's what we do, because GS is B600. So this should be B680 and this should be this. So I make Cij 0, that is that address as 0. Now I am doing the K loop. I compare K with 10. If it is equal, I go to K finish here. Jump on equal to, I go to K finish here. Otherwise, I do this. Move EAX as 10. Mul ECX. Mul is a command which will take the value in EAX and multiply with the content of ECX. So what is ECX stands for? I. So basically this gives me I into 10. And add EAX to EDI. So what is EDI? J. EDI is K. So this will give me, so I into 10 will be stored in EAX. Now this will give me EAX is equal to I into 10 plus J plus K, sorry. Right. Now DS colon EAX. Now DS, now is the point, what is DS? Now let us go here. When I am calling the matrix multiplication, I push, before I call the matrix multiplication, I push the two source segments and the data destination segment into the stack. Please note that initially the A matrix is stored in DS. My A matrix is again stored in 18. 18 is where we have stored the matrix. So let us go here. 0x18 in GDT is a read-only segment where I have stored my A matrix. So these two are the source matrices, and 0x20 is the segment in which I need to store the return matrix, the multiplied matrix. So these things I am pushing into the stack. So at this point of time, I pop, when I call matrix mel, I pop the EBX, that is a return address, and then I pop the destination matrix, because I pushed in this order. First the destination will be there, then the source 2, and then the source 1. So I pop, so ES will store the destination segment address, then I pop AX and move it to DS. DS will store the source 1, and FS will store the source 2, or DS will store the source 1, and FS will store the source 2. Sorry, it should be the vice versa. DS will store the source 2 and FS will store the source 1. Okay. So whenever I am executing matrix multiplication, if I say DS inside that, that is the source 1 matrix. So here what I am moving to the register BL, it is A of IK is now in BL, in register BL. BL is the 8 byte of register, first 8 byte of register EBX. Now again I move EAX as 10, so EAX becomes I into 10. EAX becomes 10, and mul EDI. What is EDI? EDI is K. So EDI is now EAX becomes, mul EDI will multiply the content of EAX with EDI and store the answer. So EAX now will become 10 into K, add EAX with ESI, ESI is J, so EAX is now 10 into K plus J. Now move byte BH, FS colon EAX. So what is FS? FS is the source 2, so this will store B of KJ. So BH is equal to P of KJ. Now and byte BL and BH. So I will get, so the answer would be in BL. So BL will be equal to now AIK and BKJ. Bitwise AND happens. Now I OR it with byte in, OR this value, this stores the temporary result. That's a temporary location for Cij. This is B700. So Cij now will become Cij plus AIK and BKJ. Sorry, this plus is nothing but OR. Now I am incrementing EDI. This is nothing but K plus plus, and then it jumps to K start, again it completes. So this explains how the matrix works. And after I finish one K loop, again I move EAX as 0A, multiply ECX. So what is ECX? I. So now EAX becomes 10 into I, and add EAX comma ESI, so this becomes EAX actually becomes 10 into I plus J, and GS stores the destination segment. So I am moving into DH, the temporary value of Cij, and actually I am I should say the temp value of. So now I am updating Cij completely. Right. So this is the way I do, and also note that I can't directly move byte EX colon EAX to GS colon 0x100 I can't do two memory operations in an instruction. That's a restriction of the x86 instruction set architecture. So there can be only one memory operand. I can't do so. Essentially, I'm doing it as two instructions here. Then I'm incrementing ESI. ESI is nothing but J++, and I jump to J start. Once J is finished, I'm incrementing I++, and I start. After this is over, I make my counter I as 0. Then you know that GS:0x80 is storing the return address, as you see here. Store return address as B680. That is GS:080. So I move it to EBX and I push that value into the stack and I do a return. So I actually jump to the return address. Okay, I jump to the return address. So initially what I do, I store the matrix A is stored in the segment given by the selector 0x18. I multiply, and the second source is also 0x18, the same matrix. Now the destination matrix 0x20 has A squared after this, at this point. Now again I am pushing A squared as the source 1 and A as source 2, and in 0x28 I will have the return matrix which is A cube. And after I finish this, I jump L2, that is I jump this entire routine and come to this location. Then what I do here is I go back to my original 0x10 segment. What is that 10 segment? 0x10 is a start B00 and goes to limit BFF. I go and make B plus 2, D208 as 0x DECE. So this now becomes 0x DECE to start with, and 2FF8 as 0. So this is B plus 2 is DFF8 as 0. It remains 0. And then D200 as 0x BABE. D200 as B, and D208 as CAFE. And then so then it goes, and so these are all some statements which we need not worry about now. Let us go to 159. It loads GDT from B plus 2 DFFA. So what was DFFA? DFFA was GDB's GDT. So that old GDT is loaded. Similarly, 2FF2, that is DFF2 stored GDB's IDT, and so it loads the old IDT of the GDP. So now it says jump 0x8. This corresponds to the code segment of the GDT, because already I am loaded the GDT of that, and dword fin is next. So it comes here, and then it initializes all DS, and these are all the descriptors in the original GDB, and then it says in 3, fine. Now we should know what are these code segment and the data segment in the GDT of the GDB kernel, right? That we will see once we execute it. So this is how the program basically executes. Now this is loaded. Now how do you execute the program? Till now we have just seen how it is loaded. Now we just press C. now you get some signal 6eq. This is a segmentation fault. This is again some problem with the the mimicking of the thing. So again we load it. No, there is an error. Again we load it. Now we continue. You should get a sick trap. That means the program has executed correctly. The last instruction executed was A1 E1. Right? Now we will go and see what are all the things happening here. Okay. First and foremost, let us go and see x/2x 0x DFFA. There we note that this is the place where your GDT is there. So 0017 is the GDT start, the size of the GDT of GDB, and it starts at 0x1000. Okay, so suppose S/x 2x 0x1000. Note this is a null descriptor. 1008 is the code descriptor. Please note that the code starts at 0 and its privilege level is 0 and it has a highest limit of FFFF, and so this is a code segment descriptor of the GDT. Similarly, IDT, where does it start? S/2x, that IDT value we stored in DFF2. Please note the screen here. So the IDT again had a limit of 1000, but the IDT actually started at 0. So S/2x 0x0. Right, so this is the first IDT for divide by 0. 0x8 is for the first interrupt 1. This is for interrupt 2. This is how it looks. The int 3 that we are executing, this is where we start. So these are all the interrupt table for the GDB's IDT. Now let us see what is happening, whether the code has worked correctly. 0xD200, we see BABE. D208, we should see CAFE. Right? Now we'll also see something that has happened. Let us go and see what has happened to our stack. The stack is 0xC1000. So S/2x 0x C080, because the stack pointer was set to 80. So it is expand down segment. So we should see C0 70. Yeah. As you see here, from C080, the stack has been populated. BC 18, 28, BC, and stuff like that. So you can even say S/20x C060, then we can see much more here. So the 10 BC 28, 18, BC, these are all the stack values that have been pushed into this. So we had been pushing 28, 18, as you see here, into the stack. When we were calling this, calling the stack here, please note, we have been pushing 18 and 20, etc. But then we also pushed, finally we pushed 28, 18, and this BC is the return address. If you just calculate, it will be A0 BC is where you come back here. And so this is all that, and we can also see that that return address was stored in some place. You can just see s/x0x b680. Note that this is the return address, and that is also BC that was stored there. And okay, so the matrix, of course, is going to be stored in the final segment starting at B400. That's where it is stored. Okay, so this basically explains you the working of segmentation. How do you set up segment registers? How do you convert a C code into a assembly code, and how you execute this entire framework. I hope you enjoyed. So you can now start working on this. I want you to do expand this code and do a power 5, a power 10. So what it means. So I just want you to do more exercises on this. Probably increase the size of the matrix. So these are some things that you can play with, so that you get a grip over the entire assembly handling of x86. Thank you.